Okay, so we are continuing on with graphing ellipses, and this is the example that we left off on. So here we're given an equation of an ellipse in general form, and we can tell that this is the equation of an ellipse and not a parabola because there's both an x squared term and a y squared term. If there were only an x squared term or only a y squared term, then we would know that the equation would represent a parabola. Okay, so to change this from general form to standard form, so that we can see what the center of the ellipse is and then determine what the vertices are and so on, we are going to have to complete the square, completing the square twice for both the x terms and the y terms. So I'm going to rewrite this equation. And I'm going to group the x terms together. So I'll have 4x squared plus 24x, and then plus 25y squared minus 50y. And I'm going to add 39 to each side of the equation to move the 39 over to the other side of the equal sign. And before we complete the square for the x terms and the y terms, we have to factor out the leading coefficient of each grouping. So I can factor out the 4 here. I'm going to leave a little space for completing the square, and then I'll factor out 25 from the y terms. And also leave some space, maybe a little more space. I'll have equals to 39. Okay, so for completing the square of the x terms, I'm going to look at the 6, and I'll divide 6 by 2 and then square it. So I'm going to add and subtract 9. That's the same thing as adding 0, so I'm allowed to do that because it does not change the value of the left-hand side of the equation. And then for the y terms, I'll divide -2 by 2, which is -1, and square it, so I'll add 1 and subtract 1. Now by the associative property of addition, I can group these 3 terms together and group these 3 terms together. So now I've created 2 perfect square trinomials. And those perfect square trinomials will factor, so this one will factor to x plus 3 squared. We still have the -9 there. And then this other perfect square trinomial will factor to be y minus 1 squared minus 1. And then we can distribute the 4 in and distribute the 25 in. So we'll have 4 times x plus 3 squared minus 36 plus 25 times y minus 1 squared minus 25 equals to 39. And we want to get all of the constants on the right-hand side of the equation. So we're going to add 36 to each side and then add 25 to each side. And when we do that, we'll have 4 times x plus 3 squared plus 25 times y minus 1 squared equals to 100. And then to finish getting this into standard form, we want to get 1 on the right-hand side of the equation. So we're going to divide each side of the equation by 100. So that we'll have x plus 3 squared over 25 and plus y minus 1 squared over 4 equals to 1. So now we have our equation for the ellipse in standard form. So we can easily identify now the center of the ellipse. We'll be at -3, 1. Okay, so I'll graph the center. And we know that this is going to be an ellipse that has a horizontal major axis because the denominator for the x term is larger. So we'll have a horizontal major axis. So a squared is 25, so a is 5, and b squared is 4, so b is 2. So the vertices of this ellipse will be 5 to the left of the center, which will actually put me off of the graph, and then 5 to the right of the center. 2, 3, 4, 5. So that puts me at -8, 1 and 2, 1 for the vertices. Oh, I guess that's just a vertex. And that's a vertex. And then we can have the endpoints of the minor axis by using b. So since b is equal to 2, the endpoints of the minor axis will be 2 above the center and then 2 below the center. So at -3, 3 and -3, -1. So we can actually draw the ellipse now. But for practice, let's also find the foci. So to find the foci, we need to find the value of c. And remember, c squared equals to a squared minus b squared. So we'll have c squared equals to 25 minus 4. So c is √21, which is approximately 4.6. Okay, so my foci will each be approximately 4.6, 1, 2, 3, 4, 4.6 units to the left and the right of the center. So there's one focus, there's the other. So at -3 minus √21, 1, and -3 plus √21, 1. And then it also might be nice to find the eccentricity for this ellipse. And remember, eccentricity tells us about the shape of the ellipse, and it's c over a. So the eccentricity here will be √21 divided by 5, which is approximately 0.91. So because this ratio is closer to 1, we know that the ellipse should be pretty elongated, and our ellipse does look pretty elongated. Okay, so in this example, we have to find the equation in standard form of the equation of the ellipse that has vertices at 0, -6, and 0, 6, and foci 0, -5, and 0, 5. So I suggest drawing the picture with the information that you're given. So the vertices are at 0, 6 and 0, -6. And the foci are at 0, 5, 0, -5. So that means that this is going to be an ellipse with a vertical major axis. And the center is at 0, 0. So the equation will be x squared over something plus y squared over something equals to 1. A is 6, right, because it's the distance from A is equal to the distance of each vertex from the center. So that means that a squared is going to be 36. And because this is a vertical major axis, that means 36 goes under y squared. And c is equal to 5. So c squared equals to 25, so we can use the relationship between a squared, b squared, and c squared to find b squared. So b squared equals to 11. So this is the equation that represents this ellipse. I'm going to make a different video for hyperbola, so I'm going to end this one and make a different one.